In this lecture, we're going to talk about formulating integer programs, or mixed integer programs, or binary integer programs. The idea here is that we're going to usually be given a combinatorial optimization problem, and from this combinatorial optimization problem, we're going to have to formulate an integer program. By formulating this integer program, we can start using the solution techniques that we'll develop throughout this course. The idea behind a formulation is that we're given some problem P, and we're going to write an integer program, or whatever type of program, so that two things are satisfied. The first is that the objective function of our integer program is going to be equal to the objective function of our problem. That is, the optimal solutions of these two guys are the same. But we'd like something a little bit more. We'd like to have a mapping between the feasible solutions of our integer program and the feasible solutions of our problem. Specifically, this mapping is going to allow us to have a solution in our integer program, take this solution, and map it to a solution in our problem. We'd also like to do the converse. That is, if we have a solution in our problem, we'd like to convert this to a feasible solution inside of our integer program. And every time I'm talking about a solution here, I'm talking about a feasible solution. So feasible solutions in our integer program are going to map to the feasible solutions in our problem. We're going to go through examples of how to formulate integer programs from combinatorial problems. To formulate an integer program, we can use sort of a cookbook type method. In this method, what we're going to do is identify our input parameters. We're going to take the input-output view and find out what the input is. From this input, we're going to create some variables. These are going to be our integer variables inside of the program that we're going to optimize over. Once these variables are written, we're going to write our objective function. And after we write our objective function, we're going to write constraints. This usually sounds pretty simple, but the reality is always going to be a little bit more complicated. Everyone's going to formulate these problems in a different way. They're going to think about the problem in a different way. Usually they'll end up with the same type of variables, but the method to get there is going to be a little bit different. From my experience, this is how it usually goes. Identifying the input parameters to the problem is usually pretty easy. We can find out what these are. Creating the variables is a little bit more difficult. So here, usually you take a nice informed guess. And usually the way you're going to make the guess is we're going to use our objective function as the goal. We're going to think, I need to write the variables that are going to allow me to write down my objective function in some reasonable way. If we make our guess based on this, then writing the objective function itself, after we write the variables, should be easy, an easy process. But then we come down to the constraints, and we don't know what to do all the time. And usually what happens is, we can't actually write the constraints with our original set of variables in at least a moderately complex problem, and then we have to go back and make another guess at our variables. And we'll keep iterating back and forth through this process of guessing our variables, writing our objective function, and writing the constraints. This is just a practical experience sort of thing. Your experiences may differ on how you're going to write these things. Let's go through some examples to see how we can actually write integer programs. We'll start by talking about the knapsack problem. In the knapsack problem, we can identify the inputs pretty easily. We have SI, the size of item I, VI, the value of item I, and C, the capacity of our knapsack. Now we need to take our input and invent some variables. And our variable is going to allow us to write our objective function. In this case, our variable is going to be xi. And xi is going to be a variable that's equal to 0 or 1. And we're going to have one of these for each item. And this is going to be an indicator variable. And it's going to indicate whether we've included item I in our knapsack or not. Specifically, xi is going to be equal to 1 whenever I is included. And this mapping goes in both directions. Xi is going to be equal to 0 when I is not included. The reason we picked these variables xi is because they seem natural. We're working with items that we'd like to put in a knapsack. Xi, we're going to have one variable for every item. It's going to be 0 or 1 depending on whether it's in our knapsack or not. Now we can go ahead and write our integer program. We can write our objective function rather easily. we'd like to maximize the value of the items inside of our knapsack. So we're going to sum from I equals 1 to n is the number of items, of vi times xi. We need a constraint. Our constraint is going to be that the sum from I equals 1 to n of the size of our item times whether it's included is going to be less than or equal to c. And finally, we need a constraint on our variable xi. Xi is going to be a 0, 1 variable. And now this integer program fully models the knapsack problem. Whenever we have a set of variables xi, we're going to use these two relationships, xi equal to 1 and xi equal to 0, to find whether I is going to be included in our problem solution. Conversely, if we had a solution to our problem, that is, we knew whether I was included or not, we could go back and find the xi's that are going to be 0 or 1. This is a perfect model of the knapsack problem as an integer program. The set cover problem is not going to be much different. Here we have the input to our set cover problem, and we've made it a little bit more precise. We have a universe of elements, U, and we've made it more precise by indexing all of the items in this universe. There's going to be n elements in the universe, and they're going to be indexed by j. We also have this set of sets, n. N is going to be a set of particular subsets, and each one of these particular subsets we've denoted by t, and we've indexed these t's by I. So n is going to be the set of all of these subsets. This is the input to our set cover problem. Now we need to invent some variables. In this case, our variable is going to be very similar. Xi is going to be a 0 or 1 variable. And this is going to be an indicator variable, and it indicate including the set ti. Where again we have the same mapping. That is, xi is equal to 1 means that ti is included. Xi equal to 0 means that ti is not included. From this, we can write our objective function. In this case, our objective function is going to be a minimization problem. We're going to minimize the number of sets that we're going to use. So we'll minimize the sum of the xi's, since xi is indicating whether a set is included or not. Our constraints in this case are going to be a little bit more complicated. We're going to need a constraint for every item j. And what we'd like to do is say that for every item j, we need to cover this item. To do that, we're going to sum up over all the sets such that j is included in that set. This index is going over all the sets that include item j. We're going to sum up all the xi's associated with these sets and make sure that it's greater than or equal to 1. And we're going to do this for every item in our universe. What this is saying is that if we look at all the sets that include j, that is these sets, and we sum them all up, we've included at least one of them in our collection of sets. If we've included for every item a set that covers that item, we've covered every set in our universe. The final constraint we need is that xi is going to be either 0 or 1. And this finalizes our integer program. So here again, we've taken our combinatorial optimization problem, in this case the set cover problem, and modeled it as an integer program. We're going to see these examples over and over again, and a fundamental part of the course is taking a combinatorial problem and modeling it as an integer program. So we'll get a lot of experience with this.